All right, thank you. All right, my apologies for the little delay. I hope I can make it up with an interesting presentation. So my name is André Weiner. I'm from the Technical University of Braunschweig. And today I'm going to present to you results produced by myself and by my supervisor, Hrvoje Jasak, about how to use dynamic mode decomposition to analyze some compressible effect called transonic shock buffet on a NACA airfoil. All right, I'm going to talk about a little bit the buffet phenomenon itself, and then I will very briefly show you how you can simulate that in OpenFOAM. And the main part will be on how to properly use the right variant of dynamic mode decomposition. And I hope this is really going to be useful for anybody who wants to really use dynamic mode decomposition on realistic flows involving scale resolved turbulence and things like that. So I think this can help you, save you a lot of headache. And then finally, I will show you some results I find quite interesting. All right, here we go with a simulation of the transonic buffet phenomenon. You see we are in transonic flow conditions, Mach 0.75, and we are at an angle of attack where we see these kind of shock boundary layer interactions. So you see we have the shock moving back and forth, the front part of the airfoil, and we have the boundary layer periodically attaching and then detaching from the airfoil surface. So this is called, in a nutshell, the transonic buffet. And I'm investigating this kind of phenomenon together with other researchers in a project, FOR 2895. If you follow the link on top of the slide, you can find more information. So this project does not only involve numerical simulations, but also a bunch of different experimental facilities like IPSP recordings, PIV, Schlieren, and I'm the modeling guy basically. So everything that I'm going to tell you about today works for CFD, but it also works for PIV and Schlieren data and whatever you have. All right, a few words on what actually modal decomposition means, because it's like not such an intuitive name, I would say. So imagine you have snapshots from an unsteady flow, you have your flow fields that are changing over time. And what modal decomposition does in general is it takes those snapshots and then it separates them into something that is changing in space, but not over time. And then another part that is only changing over time, right? So that makes this decomposition between changes in space and changes in time. And commonly, when you want to really apply dynamic mode decomposition to real flow with all sorts of problems, noise and turbulence, which is some sort of noise, you are confronted with the following questions, which I would like to answer here during the presentation. So the first question would be, which kind of flow fields or derived flow fields to put in your state vector when building the data matrix? Then the second frequent question is, transient simulations, unsteady simulations, they require a lot of computation effort and produce a lot of data. And the question is, how to estimate how much signal you need and how many samples you need. Then finally, there's one main parameter of the dynamic mode decomposition, which is the number of POD modes that you use as a basis for the DMD. Right. And of course, I did this little benchmark study because there are many different DMD variants out there. And of course, every variant is the best one. But if you really want to use them and you find, okay, I get very different results once I change a tiny parameter, or I change the data a little bit, or I use a slightly different variant, that's really annoying from my point of view as a practitioner. So I'm going to show you what I would think can be discarded today. Right, just 2 slides on the simulation approach. I simulated this using the ESI version 2012. The solver there is CentralFOAM. It uses IDDS modeling for the turbulence. So we have some turbulence scales resolved, and the runs closure is done with Spalat-Almaraz turbulence model. And I performed 2D and also 3D simulations. 2D simulations are nice if you just want to get a feeling for what could potentially happening for a little low cost. And everything that I'm going to show you today is available in the GitHub repository you see linked at the bottom of the slide. Here's just a short view of the mesh. It's a block structured mesh of the NACA airfoil. It's basically two-dimensional mesh that is created and then extruded in this bandwise direction. All right, let's get to the dynamic mode decomposition. So if you go through the DMD literature, you find at least, I think, like 20, 30 different variants of dynamic mode decomposition. And to put everything a little bit into an order, I created this kind of categorization of 5 different categories, which helped me to focus on, isolated parts. And my focus is more on reducing the sensitivity to hyperparameters and to noise. So I'm not looking at variants that are mainly developed for increasing the accuracy of the model, like in terms of reconstruction accuracy. So if you want to get a more comprehensive overview of all the different DMD methods, you can have a look at this review paper by Peter Schmidt, who is also the person who originally developed DMD. All right, here we go with the first 3 categories. So the starting point of every DMD and modal decomposition in general are data matrices. So in the first data matrix X, we have all but the last snapshot. And in the second data matrix, we start from the second snapshot and go to the very last available snapshot. And already here, there's some variety that you can use, which is not directly visible in this overview, but you can imagine that inside this very long column vector X, you can put velocity, you can put derived fields, density in case of compressible flows, for example. Then there are some variants for the singular value decomposition in particular that allow you to remove some of the noise in the data. So some, let's say, sparse structures in your data that you're not really interested in when you're looking at coherent structures. But this is let's say, optional. It can be considered as a kind of pre-processing, which is why it's in this dashed kind of box. Then comes the main definition of the operator. So on the very left, you see the standard definition of the linear operator A that maps from X to Y in the least square sense. So this is the standard definition of DMD. However, more recently, people have started to try to build physical laws into physical principles into this operator A. And one principle is, for example, that you make A unitary operator, such that basically A conjugate complex transpose A gives you the identity matrix. And this is equivalent to assuming, for example, if your state vector encodes some kind of energy, this is like energy preserving. This is like an energy preserving operator, okay? And finally, there's another variant called the optimized DMD, where you directly, instead of computing the operator A, you directly try to compute the eigendecomposition of the operator, which is like nonlinear, non-convex optimization problem, and in general really hard to solve. Okay. Now the second part, the first is duplicated. This is still the operator. Then the last 2 parts are also quite important. The first one is, how to, in the kind of FFT sense, associate each mode with an amplitude. On the very left, you see the standard definition of which results from a system of ordinary differential equations. So this is like the initial condition basically. And this is, as I said, the standard way. There's also another way to optimize the coefficient vector B and an additional step after computing the operator, which is commonly called optimal DMD. And then there is another extension of this idea by introducing like an L1 norm term in the optimization problem to force as many of the B coefficients as possible down to 0, right? And then the last and very important portion of the algorithm is how to select dynamically important modes. And again, the standard version you see on the right, you just take for every mode, you take the corresponding coefficient in the B vector, and a larger B is better, basically. What's more important? Then another interesting variant is here on the right side, which deals with the effect that sometimes you have modes that are very quickly vanishing. They have a high amplitude, but then they are, during the time resolution, very quickly vanish. And this integral kind of criterion takes this into account by integrating up the importance of B over time. Okay. And in the results section, I will use a couple of abbreviations. So TDMD would be like total least squares pre-processing, and then standard DMD. UDMD would be like operator DMD with the unitary constraint on the operator. Optimal will be optimal mode coefficients. Integral will be integral importance measure. Amplitude will be the standard way to measure importance. So for example, if you have opt DMD int, it will be total least squares DMD with optimal amplitudes and integral mode selection. Okay, I hope you keep that in mind. Okay, so let's go through some tests that I did. The first one is I tried different state vectors, so different flow fields, but also different sources of fields. For example, if you consider that with IPSP, so this is like surface pressure of airfoils, or PIV, you only get information in a plane. And one question is, are the spectra I get from these data, are they comparable to what I get from a volume field in the CFD simulation, for example? And another question is, of course, if I enforce a unitary constraint, I also have to make sure that my actual state vector fulfill these constraints, right? So that they're actually constant in time. So what I did here is I looked at the norm of the state over time for different types of state vectors. So the first one is like taking the pressure coefficient from the surface. And you see this is obviously not very constant over time. It changes by about 10%, the norm. So here it wouldn't make sense, it wouldn't be sensible to actually use this unitary constraint. And also there's no real reason why the pressure on the surface should be constant, like the norm of the pressure. Second one is the density. And here I have two variants. One is just the raw density field coming from the CFD simulation. And the second one is weighted with the cell volumes. And you see here that it's really important to weight the state with the cell volume in case of volume data, or with the area in case of surface fields. Because first of all, intuitively speaking, you do not want to see your mesh in the analysis. And we're always solving least squares problems. So if your mesh has different densities in certain regions, this will also modify the least squares problem. And second of all, it comes also from like a mathematical point of view, from the definition of the norm itself. All right, then another state vector is the velocity field. So basically, if you take all the three velocity components, what you get is the kinetic energy if you compute the norm, or actually you get the square root of the kinetic energy in this domain you're looking at it. And you see this is already much more constant, but because we have a compressible flow, like kinetic energy itself is not perfectly conserved. And you can actually, by assuming isentropic flow, can arrive at a state vector that uses velocity components plus the sum factor times the local speed of sound. And you see this kind of norm is really, really constant over time, so it changes by less than like 1% or 0.1% actually. All right, so this state vector will be suitable to apply the unitary constraint, for example. Now, the first and most critical test is basically how sensitive is my result to the POD basis I select. And what I did here is I look only at the most dominant mode, which is the buffet mode. And we look here at a very zoomed in view of the unit circle. And you see only like the most dominant eigenvalue for a bunch of different values of the POD basis. And ideally, what you want to see is that, all these points, they cluster up in a certain point, because then my sensitivity to rank is really low. And what you see, for example, is that if I use the amplitude criterion, I get a huge scatter. Instead, if I use the integral criterion, my results are much more consistent, especially for the version with unitary constraint, but also for the other two versions. Now you see, if you look at the optimal DMD with integral criterion, but also at the TDMD, that most of the points are clustered in a certain region, and then there are just a few outliers. And my question there was, okay, let's jump over this. My question there was, okay, if the rank, if these problematic eigenvalues occur at very high ranks or at very low ranks, then that's still something I can deal with, because then I can just say, okay, select the rank somewhere in the middle. And what you can see here for the DMD and for the TDMD is that basically you get these outliers for very high values of the rank for very large POD bases. So essentially, if you do not chop off enough of the turbulence or noise that you have. And what this dashed line indicates here in the middle of all the three subplots is the rank that you get from an algorithm called singular value hard thresholding. So this basically takes away the burden of choosing the right POD basis. And as you can see, this kind of optimal rank gives you a good value where you get relatively stable leading eigenvalues. All right. Then another frequently asked question is, like, how many samples do I need and what happens if I do not have enough samples? And what you see here is that, for example, here the dashed line again, the dotted line indicates the buffered frequency. And what you see here is that even if you have very few samples, then we still can capture this frequency quite well. But if we look at the, at the modes at higher frequencies, you see that they are kind of clustering up at the upper theoretical bound of the frequency due to the Nyquist criterion. And probably you have some kind of aliasing effect that the high frequencies, they will be flipped over into another region. So you will get modes associated with the wrong frequency. And another test that I did is, rank sensitivity of the full spectrum. And what you see here is that, for example, if I take the density, I have a quite strong influence of the rank parameter. So what you actually see here is every column here indicates the spectrum of one DMD. So there's a little bit like a DMD spectrogram, and the different markers are scaled with the importance, the integral importance. And the 10 most important ones are actually colored in red. So you see basically most of the important modes are somewhere here around the buffered frequency and then the harmonics of the buffered frequency. Now instead, if I use the, let's say, state vector encoding some physical ideas, you see that even for quite small POD bases, I get relatively consistently important coherent structures at frequencies of about 8 to 10 there. You see like a red line, and about 12. So the way how you construct your state vector significantly reduces the sensitivity to the rank, can reduce the sensitivity to the rank. All right, and summing up this little snippet of information, what I recommend is basically to put as much physical intuition in the state vector as you can. And then I don't see any value in additional pre-processing, at least for numerical data. But I found similar results also for experimental data. And use the standard operator definition, optimize the amplitudes, and use the integral selection criterion. This is also what I did to show you some of the results hereafter. So if you followed the training session on Monday, you know that there's more to the DMD analysis than just performing the DMD. You also have to a priori, figure out where there are regions of interest and get some idea about the spectrum that you are expecting. And here I took some probe locations to identify, the frequencies for associated with vortex shedding. And this tells you basically how frequently you have to sample if you want to capture all these phenomena. Here is the spectrum, this time coming from the DMD. So this tells you where you have dominant DMD modes at which frequencies. See, there's the buffered frequency, but then there are also some interesting frequencies over here, 8 and 12, which we already saw before. Here's just two selected modes. On the top row, you see the buffered mode, and below that, you see a vortex shedding mode. And very interestingly, you see this kind of lamella-like structures. And if you're not familiar with DMD, this doesn't tell you much probably. But if I now show you a little animation, you will immediately understand what these lamella-like structures are. So you see they are basically acoustic waves traveling from the rear part of the airfoil towards the front part. And this is, one question that is frequently discussed in the literature. So what is the influence of acoustic waves on the buffered phenomenon? You see also, for example, that the waves traveling upstream on the lower side, they originate more from the trailing edge, while the ones on the upper side, they originate more from the shear layer. And another interesting result is you can, at least in terms of CFD data, I could take surface data, volume data, slice data, and I got very similar spectra for all the different data sources. All right, if you are in general more interested about data-driven techniques, we have a data-driven modeling special interest group, which you are free to join and learn about these kind of techniques. And that's everything I have for you. I hope I could almost catch up the time. Yeah.
Thank you very much. Questions?
So if you construct a specific norm it will be actually conserved as you put in this information, and what's the gain in using this? I mean, then you know the system costs. Just to see how much noise you have in the system.
Sorry, just repeat the question.
Okay. So the question is essentially, what is the value of having like a norm including some physics, right? Okay, so
if it's constant, if you make it constant, then you actually know it's constant. So where is the dynamic?
Okay. So this is more like an integral criterion. So this is, for example, preservation of the kinetic energy, like in a big control volume. Like still the flow, like inside that volume can change over time periodically. And one common problem is the sensitivity of DMD to little changes in the data. And what you very often find is that you get eigenvalues that have a magnitude slightly smaller than 1. So they are like very quickly disappearing. And with the unitary constraint, you can actually enforce them to be on the unit circle. And another side effect is that also the sensitivity to other hyperparameters is reduced. Yeah.
Thank you for very nice work. I have a question about DMD. Is very good at that. So it's separate different frequencies as well. The nodes at the end are not optimal. So it's kind of difficult to use them as a predictor for the nodes. And then the output to what we use the records of DMD. You have any example how your node, space nodes, and your results change basically in space plus standard. Maybe well, a little bit more host there.
Right. That was a very long question. I hope I can repeat that.
Choose the bit you want to answer.
Yeah.
Okay. So in a nutshell, the question was about the usefulness of DMD for reduced order models, and what might change in that respect when using different DMD variants. Okay. So first of all, I have to say I only use DMD so far as a kind of analysis tool, because from my point of view, the accuracy that you get from DMD reconstruction is not very good. So I wouldn't use it as a reduced order model tool. And another interesting point is that if you change the rank of the POD basis, you may also get like similar spectra, but very often the modes change, as you just mentioned it. And so this is like something really non-intuitive, and I have no insight how to how to find the right path there. So, but like I think, DMD has a great advantage of being very transparent. So it's very simple, mode, frequency, you know what's going on. And instead, if you really want a reduced order model that aims for accuracy, then I would for sure go for a combination of POD, where you get the orthonormal modes, and then some kind of machine learning technique for the temporal evolution. That's a common way to do it, to also yield quite accurate results. Yeah.
Anyone else questions? Please, I'd like to speaker again. Thanks, Andre.
Thank you.
Grab that mic.
Perfect. Good morning, everybody. My name is Hrvoje Quixley, and I'm an aerodynamics engineer at FT Technologies. And today I'm going to be taking you through an aerodynamic analysis of one of our FT ultrasonic wind sensors. So as a brief agenda for today, I'll take you through an introduction of who we are at FT, what we do, why we do what we do, as well as the dominating aerodynamic phenomena that we expect to see for one of our sensors. On the right-hand side is the FT742 flat front sensor. And I'll go through the CAD geometry as well as the simplifications we've made, the computational domain, as well as the meshing procedure, and then the CFD settings that we've implemented, followed by the results and discussion with a particular focus on the K-omega SST and the K-omega SST gamma RE theta models, and then go on to the steady state versus transient assumptions before concluding. So as an introduction to FT Technologies, we're a company that designs, manufactures, and produces ultrasonic wind sensors that measure the speed, direction, and temperature using our patented AccuRes technology. So to run you through how this technology works, we've got 3 transducers that sit inside the top portion of our sensor. They generate ultrasonic signals. These run for a few milliseconds before reaching resonance. And once resonance is achieved, the AccuRes technology is able to monitor the phase difference caused by the internal cavity velocity. This allows us to operate at a range between 0 and 90 meters per second and a temperature of -40 up to 85 degrees. Now, all this is possible with our in-house cluster. This allows us to run aerodynamic as well as acoustic simulations. Here's a brief overview of what an acoustic simulation looks like, the sound pressure level inside of the cavity. And precursor to this is we need to run our aerodynamic data in for any initial conditions. So what are the dominating aerodynamic phenomena that we expect to see? Well, our sensor can be simplified as to 2 circular cylinders with a cavity in the center. So referring to the literature, we can simplify it to a 2D or 3D canonical problem with an operating Reynolds region between 0 and 330,000 Reynolds. So according to Hrvoje's flow regime research, this puts us in the subcritical to critical regime, where we would expect a transition between laminar and turbulent flow. As for the physics that we expect to see, there's flow separation externally as well as internal. There's vortex formations such as tip vortices and von Karman vortices, and then a jet due to the Venturi effect inside of the cavity, which will then interact with the wake. So what were the main drivers of this study? Well, coming from industry, there's a constant compromise between the computational cost and the accuracy of the high fidelity methods that we use. With this in mind, we've chosen RAMS as an approach with a K-omega SST and K-omega SST gamma RE theta models. This is a benchmark to study the effectiveness between a fully turbulent assumption and a laminar turbulent transition model. Also, we need to develop an aerodynamic database that can be fed into the acoustic research framework. With the overall aim of our research is to understand the flow field inside and around our sensor. So what does the CAD geometry look like, and what simplifications have we done? We've removed all the grooves and the notches, smoothed out the whole surface, and we've simplified the pillars and the supporting mount. So on the left-hand side, you've got our full FT742 flat front. On the right is our simplified model with the full CAD, well, not the full, the simplified CAD geometry. There's some stuff I can't give you away, but there you go. As a sense of perspective, our sensor is 55 millimeters in diameter. So for our meshing procedure, we've taken snappy hex mesh as an approach. This approach allows us to segment our geometry into patches. This enables us to refine the surface mesh where needed, monitor the Y+, as well as the forces acting on the sensor itself. So our computational domain has a standard inlet and outlet condition with slip conditions all the way around and no slip on the surface. The reason for the size of this domain is we don't want any interaction to happen. Well, we don't want influence from the boundary onto the sensor itself. So an overview of the mesh topology. Here you can see there's the refinement in the wake as well as the refinement inside of the cavity. We have approximately 300 nodes horizontally and 100 nodes vertically, and we've got a refinement around the sensor of around 0.25 degrees. This allows us to capture the separation point within a high degree of accuracy. So to run over so that we use, 3 meshes have been created between 7 and 15 cells. They're hexahedra dominant, and we've got a non-orthogonality of around 65 degrees. And for all the cases, we've got a y plus similar to 1 for the current of 10 meters a second we're running. So to go more into the detail of what the mesh looks like, we've got our level 0 with a cell diameter of 39 millimeters with 5 cells in between each layer. Further refinement in the wake going down to 1.2 millimeters at level 5. And then once we get inside of the cavity, we've got a level 8 of 0.15 millimeters. This then feeds into our boundary layer, where we've achieved 5 layers of thickness, with a first layer thickness of 0.1 millimeter and an overall thickness of 0.34 millimeters. So what are the CFD settings that we've used? Well, we've used OpenFOAM version 2112, and for our pressure, we're using a GEMG solver to solve the linear system with a Gauss-Seidel smoother. And then for our velocity, turbulent kinetic energy, dissipation, and gamma and RE theta, we've got smooth solver as well as a Gauss-Seidel solver. Smoother, sorry. With our steady state, we've got a simple C method that we've implemented with a single non-orthogonal corrector. For our transient solutions, we've chosen the piezo method with 2 non-orthogonal correctors and 2 pressure correctors. Now, for the spatial discretization, I'll make reference to the first and second order that we've used. The first refers to a Gauss upwind scheme, and the second refers to the Gauss linear upwind scheme. We've only implemented the spatial discretization for velocity, not for any of the turbulent properties. So what's the test case that we're looking at today? Well, we've got 10 meters a second, around 36,000 Reynolds, and a turbulent intensity of 0.14%. So very low turbulent intensity. Some post-analysis between the SST and the SST-LM, we've seen about a 30% increase in the time taken for any mesh for iterations per run. So moving on to the results and some discussion. We'll look at the flow field features, particularly the surface pressure coefficient, as well as the skin friction coefficient, and the horizontal and vertical velocity profiles inside of the cavity. What happened? Oh, there we go. Okay. I'll assess the mesh convergence study. Oh, sure. Yeah. Going on to the results of the discussion. The flow field features, looking at the surface pressure coefficient, the skin friction coefficient, the horizontal and vertical velocity profiles inside of the cavity, and then we'll assess the mesh convergence study, the effects of the first and second order spatial discretization, effects of the turbulence model, implementing a symmetry plane, and symmetry versus transient. And here's an overview just of what a table looks like. So this is a vertical cross-section through our domain for our SST second order steady case. Here you can see the effect of the downwash in the wake of the cylinder, as well as the acceleration in the cavity itself. So once we get a little bit closer, you can see there's 3 recirculation points at the top, center, and just the support of the sensor itself. And then inside of the cavity, there's 3 more recirculation regions. And once we take a cut through the central point of the cavity, you can see the wake of each 6 pillars and the interaction that has with the wake and the downwash as well. So here's a surface pressure coefficient plot, surface of the sensor. You can see the stagnation point of the support, as well as on the sensor itself and on the pillars. Next is the mesh convergence study. So the parameter that we use to monitor the mesh convergence is the skin friction. So here on the left-hand side, you've got the SST model, and on the right-hand side is a SSTLM model, the gamma RE theta model. And on the x-axis, you've got the degrees, so 0 representing the stagnation point, with 180 degrees representing the backside of the cylinder. And we've plotted all three meshes for first order spatial discretization. So once we move this over to second order, you can see there's a convergence of the meshes to a similar solution in separation point of around 80 degrees. This corresponds to a laminar transition, or a laminar separation, excuse me. So with this in mind, and in the interest of time and saving computational costs, we selected the second order mesh, mesh 2. So going through sections sensor itself, at the top portion, you can see there's a separation point close to 80 degrees. And on the right-hand side, this is a coefficient of pressure plot taken at the same point. The main takeaway of this is it's a sanity check to say, okay, are we sitting at the same separation point that we expect to see? And it also gives an indication that there's some unsymmetric nature to the flow. Moving down to the next portion, the big takeaway here is that there is a shift in the separation point from 80 to 90 degrees, turbulent flow around this region of the sensor. And then moving down further, shifted back to a laminar separation point of around 80 degrees. Okay. So moving to the symmetry case, here, with the interest of time, we wanted to see if we could reduce down the computation time any further and how that would affect the results. So here are the original cases that I presented to you earlier. And then once we overlay the symmetry cases, you can see they're virtually indistinguishable. So from a quick and dirty simulation, it does, initially it looks like it does the job. So then moving on to the unsteady cases. Here again, we wanted to see what the difference would be in separation point as well as the coefficient of pressure. Again, there's not too much difference in the simulation. So what this tells us is we can run unsteady, but we can also run a steady, and we can also run a symmetry. And in terms of separation point, they look fairly similar. So if we take a horizontal slice through the cavity, what is the velocity profile we expect to see? This is very important for us to feed into our acoustic engineers so that they understand what the initial conditions they need to run. So for what you're seeing on the left-hand side is the cut through the center, as you can see here, for the steady SST, and SSTLM steady cases. So once we overlay the unsteady simulations, there's a larger difference between the models as opposed to the difference between the steady and the unsteady simulations. Finally, these are a series of vertical slices taken through the cavity. You can see the progression of the flow and the difference between the SST and the SSTLM in red. So first of all, you're seeing a brief region before parabolic velocity profile is beginning to achieve. And yeah. So what are the conclusions that we can take from this? There's 3 areas of recirculation that we can see inside of the cavity, as well as variable separation points observed along the sensor itself. The mesh, second order spatial discretization for velocity is required with approximately 10 million cells. Seems to be sufficient to capture separation regardless of the turbulence model that we've observed. As for the turbulence models, the K omega SST and the gamma RE theta predict a similar laminar separation point across different regions of the sensor. SST gamma RE theta being highly dependent on the mesh size. With regard to the symmetry, comparison between the full model and the symmetry provides a similar skin friction and pressure as well as the velocity profile. For the steady and the unsteady, there's no noticeable difference in the separation point. However, there is a magnitude of difference between hours and days for the CPU time. And that concludes my presentation. Thank you very much.
Questions?
Yeah.
Just ask me to repeat.
I'll repeat it, yeah.
So I didn't quite get how to plan this. So what do you do with like to calibrate the sensor, or is it like to optimize the design to 1,000 or 1,000 inputs?
So, oh yeah. So the question is, what next, right? What does this research say, and where does it go forward from there? This is an initial set of research that we wanted to present to you. There is further research that we've continued. There is a limitation to what we can show you, obviously with the industrial nature, but I'll tell you that, yeah, there are lots more things going on, and we're investigating the effectiveness of the SSTLM model. If we needed to change it at all, if we need to monitor, or not monitor, if we need to change the particular parameters inside of it. It's also what we see in production. What we get back from production somewhat leads our research. Yeah, that's all I'll say for now.
Yes.
Why for the cells between the layers? It was more of, I think the reason we used 5 was just to gradually change the mesh because we're going from 39 millimeters all the way down to 0.1 millimeters. We wanted to have a gradual change. We do see oscillations in our results, so we want to be able to capture that as best as possible. So having a large difference between the small size and the cell, it made sense to increase it without going overboard and setting it to 7 or 9 or 11 or however many. Yeah.
You mean the transition between levels? Between different levels, right? Yeah, it grows exponentially. So going above 5, the mesh may jump from 15 million refine to 20 million refine. And you just have to refine the area that more intensity of flow. We have a 3, 5.
I don't think we went up to 7.
Doesn't change much on the background, but we just follow the best practices from OpenFOAM. Always recommend use 5 to have a smooth transition from the background to.
I guess there's number of things you can try, right?
It's really a compromise between the CPU time and the quality of the flow.
So to reiterate for people online, we went with 5 because we didn't want to go overboard with the number of cells, reduce the CPU time, as well as not sacrificing the accuracy.
Any more questions? Okay, thanks, Jordy.
Perfect.
Okay, I hope everything is in order. So a very good afternoon or good day to you, wherever you are. My name is Benjamin. I'm a research fellow at the Singapore Institute of Technology. So unfortunately, I would love to be there to present physically, but something came up and I cannot be there. So I'm presenting all the way now from Singapore. I hope the internet connection is fine. I hope I hope you can hear me clearly and see my slides clearly. So the title of my talk today is about the Bluff-Body wake entrainment of a surface level contaminant release. So this is the work that we are doing in partnership with our colleagues at DSO National Laboratories. So DSO stands for the the Defense Science Organization. And so as the name already suggests, the work that we are presenting today is somewhat sensitive in nature, but it has already been approved and taken out of context. So forgive me if I have to be a little bit vague with some of the details of the work. So on to the presentation outline. So a fairly typical outline you see here. So first off, I'll go on to introduce the motivation behind the work. So the work that you're going to see is highly applied CFD work with regards to urban or building dispersion of contaminants. We'll go through a bit of our research objectives for both CFD and experimental work. Of course, the numerical and experimental methodology that we use for both OpenFOAM and the wind tunnel at our university. Some results and observations, the summary and impact of our current findings on this urban contamination and pollutant profile, and also the upcoming and future work. So if I may. Okay. So now on to the introduction. So the distribution of wind flow patterns in an urban environment can affect pollutant dispersion and transmission. So for example, like if you were to look at the top right, here we have a cluster of buildings, and upwind, somewhere upwind, these two high-rise buildings, we see a particular dispersion pattern of an isosurface of a contaminant that is propagating downwind onto a cluster of buildings, so to speak. So in this case, the wind is blowing from the bottom right to the top left, whereby the presence of these two bluff bodies actually affects not only the wind flow patterns, but also the propagation and convection of the pollutants that are in this so-called city. So these buildings are typically shaped as bluff bodies, which, like I said, act as obstructions to atmospheric flow. So as these tracer gases follow the streamlines or the path of this atmospheric flow, they actually move or meander their way around the city. But one thing that we observe in some of our preliminary results is that these bluff bodies, right, they shed their own shear layer instabilities, of course, and these shear layer instabilities actually convect and roll up into vortices in their wake downstream. So this wake actually feels, sorry, if I may just correct myself. So this, the tracer gas or the pollutant that actually released in this city actually convects with this wake and actually fills the void that the bluff body actually leaves behind. So this results in an entrainment process, right, of the surrounding fluid, especially if the contaminants are nearby the bluff bodies. So what we observe is that, like in the isosurface and the streamline show, that there's a certain verticality in the convection of the flow. Because a lot of the work presently actually only studies the horizontal profile of contaminants or convection throughout the city, but not so much on the vertical extent of pollutants and contaminants. So say, for example, if you have someone living on the top floor of this building with a nice view, but unfortunately if there was a contaminant that's released at the ground level, what we will see is that there is actually a vertical propagation of this contaminant due to wake entrainment up to his apartment, so to speak. Right. So then again, a lot of the work that we see here is applied research, and some of it is taken out of context, you know, just to protect the sensitivity of the work. So now moving on to the motivation of the work. So because of increasingly urbanized areas, right, leading to a proximity between residential and industrial locations, there is an imminent or inherent risk of accidents or acts of mischief, which can actually cause harm to personnel, both personnel and property, if there were to be any, you know, accidents or acts of mischief. And many present studies, like I mentioned, have successfully modeled ground level contaminant behavior, right? So that's where they show, for example, a bird's eye view, and we see how the contaminant actually moves through a particular city layout, for instance. And what we observe is that a little bit more on the results here, a little bit more on the preliminary results here. We see some surface level leakage accident beside the building that has this potential to convect and move up vertically. So this vertical behavior, right, or this height-wise behavior of the contaminant spread is what we feel is an area that is worth further exploring. And on top of that, we are currently performing on-site building scale, physical tests where these observations are currently being observed. So we do simple bubble tests to see how the bubbles actually propagate for a given prevailing wind condition, because of course this is weather permitting. And then we see that, you know, in fact, these bubbles or these streamlines actually move up the building height. Okay, so now for our research objectives and conditions. So we wish to study the impact of a bluff body wake on a tracer gas, and with a focus on the vertical wake entrainment. So the observations that we see are primarily done in CFD, but some studies are also done in experiment with regards to a validation in the near wake profile. So for this image on the right, we see an incoming wind or a free stream moving from right to left, and then a vertical velocity probe is measured in the near wake region, about half a characteristic length of the building, of the leeward side of the building. And then we have a contaminant release point that is about 20% the characteristic length of the building. So the test conditions are at a Reynolds number of about 22,500. The flow is assumed to be fully turbulent, incompressible, and isothermal for now. So again, I just want to emphasize that a lot of the work that you see here is still very much in progress. We are also currently working on things like multiple bluff bodies. So let's say you have 2 or 3 buildings in succession, and also different building shapes. So for example, different aspect ratios. And also there's also ongoing work with experiment, both wind tunnel and building scale physical experiments. So for the wind tunnel experiments, we are using our low speed wind tunnel at SIT, the Singapore Institute of Technology. So this is a low speed open loop wind tunnel with a test section dimension of 0.8 meters in height and 1.2 meters in width. The test section maximum speed is up to 45 meters per second, but to achieve the relevant Reynolds number that we are looking for, this speed is set at 5 meters per second only. And the objectives of this wind tunnel test is to measure the near wake velocity, just less than one characteristic length behind the geometry. And hopefully with LDV and the smoke particle visualization, we can capture some of this behavior, but this actually proves to be quite challenging, which I'll talk about more later. So the measurement technique that we have chosen is LDV, laser Doppler velocimetry. So the reason why we chose this is because it's non-invasive, meaning that the probe, there isn't a physical probe inside the test section that would affect the flow field, because we are measuring something that's so close to the object itself, right? So anything like, say, for example, a pitot-static tube would actually most likely interfere with the results that we are trying to capture. Okay, and then like I mentioned, there's also a few building scale experiment, which unfortunately I cannot show pictures of because the location is fairly sensitive. Okay, so that's for the wind tunnel methodology. And moving on to the numerical methodology, which is the OpenFOAM part of things, the flow is assumed to be fully turbulent, incompressible, and isothermal. So for the OpenFOAM solvers, we have chosen the simple foam and piezo foam solvers with a passive scalar implementation for the visualization of the pollutant or tracer gas. So in our case, presently, we are assuming for the pollutant to be neutrally buoyant, meaning that the pollutant is not expected to affect the bulk flow of the ambient wind. So and if necessary, our simulations are also conducted with an atmospheric boundary layer as a domain inlet. So at the domain inlet, we have a logarithmic boundary layer coming in with a reference speed of 3 meters per second at 15 meters height. Yep, so this is the respective formula. I wouldn't be going through this. So that's for the first part of the numerical methodology. And for the second part, we go on to the mesh. So in this case, the mesh is conducted again using OpenFOAM utilities. So we are using block mesh and snappy hex mesh. So the background mesh, like you see over here on the top right, is achieved with block mesh. The background mesh is graded towards the middle where the geometry actually sits. So the image at the bottom here is a close-up view. So we did actually a cell grading. We split the domain into 3 different directions. So just to concentrate the cells towards the center of the domain, because we don't want to waste any cells. And furthermore, inside this refinement region, so the one that you see, I hope you can see my cursor. So the one that my cursor is highlighting is the one that's done with block mesh. And then there's a further wake refinement block that is done using snappy hex mesh with this little point here as the tracer gas source. Okay, so the grid resolution for the background mesh is 180 by 96 and 96. And the wake cell size, so this little block that you see inside here that encompasses the geometry, has a cell size of about 2.5% the characteristic length of the building, which brings us to a total cell count of about 2.5 million. So the turbulence models that we have explored are the realizable KE model, the SA DDES model, and a Smagorinsky LES model with the respective schemes that you are seeing below. So the schemes are nominally second order, so nothing too fancy, I would say. Oh, and with a maximum Crowell number that's limited to 0.5. So this is a fixed time step, but with a maximum Crowell number of about 0.5. Okay, so now on to a little bit more of the results. So the validation is done in a few parts. So we got some students to help us with this. So the first step of validation that we did is with a two-body problem, meaning we have a building one in front of the other, separated by some distance. And we look at the streamwise velocity magnitude that is measured both in front, in between, and behind the buildings. So the results that you see on the screen now are done with the realizable KE model. And it shows a fairly good correlation. So the three curves that you see here are the curves. So the flow is going from left to right in front of the front block, in between the two blocks and the one trailing the block. So these results are fairly, I would say they are quite satisfied with them, considering that the one that you see on the screen here is with the RANS realizable KE model. But of course, knowing that it's a eddy viscosity model, right? We see that there's a bit of a dampening and early recovery of the wake velocity in the results. So that's quite expected. And we do not have the results to show yet, but for now, you just have to take my word for it. For DES and LES, the results correlate much better. Yeah. So again, those are the schemes that we use to get these results. And now moving on to some observations that we see in the CFD domain. So what we are looking for is the isosurface contours to basically visualize the tracer behavior, right? And to observe that whether the physical phenomenon, like I mentioned, the bubble test that we did physically, actually can also be observed in the CFD. And we are looking at them at different concentration thresholds. We wish to observe the transient behavior of the gas propagation and also the vertical wake velocity profile in the near wake region. So as you can see here, this is the results that we got comparing the LES and the LDV results, the black points being the CFD result, LES CFD results, and the red points being the LDV results. So these are measured at 5 locations vertically from the base of the block up. So the wind is going from right to left, and then we are measuring, this is a dimensionless height of about starting from 0.2468 and up to the same height of the block. And this is the resulting result that we get. So as you would expect, the flow is highly unsteady in this region. We see a very large standard deviation. So, and of course, measuring such a turbulent result with LDV also comes with its own challenges. As you can see, there are certain outliers in the results. Although the measured LDV data actually falls within the standard deviation, I don't think this is that good of a comparison because as you can see, the standard deviation is so large, right? It doesn't really tell us much. But anyway, moving on to the tracer content of the flow. So what we have is a video. If I can get this to play. There we go. Okay, so once again, the release point is here. The flow is going from right to left. And these are isosurface contours of 1 part per 1,000, so 1e minus 3 by parts. And we can see that as the flow develops, right, we see some kind of a vertical convection of the tracer gas, although the flow is dominated by the ambient wind. So now this is monitored up to 275 convective time steps. So this is about halfway through the observation period that we're looking at. But if I were to just restart the video, so if I were to just restart it, you see that in the beginning, we see some kind of wake entrainment, and then the plume actually spreads vertically and over the building. So these are isosurfaces that are captured at 1e minus 3. So evidently this already shows this already agrees with some of the observations that we have in the physical side. So now if we move on to a smaller concentration by parts, so this is 1e minus 4. So this is 1 part per 10,000. Yeah, we should expect to see a larger cloud. And we see that as the flow starts to develop, right now the entire wake of the Bluff-Body is actually engulfed by the tracer gas. So although the release point is on one side of the building, we actually see a similar concentration by the same order of magnitude on the other side of the building, which is quite, yeah. So if this were to be an accident or some leakage or something, for instance, this becomes a problem. All right. So the images that you see on the left are instantaneous snapshots showing the actual behavior of the tracer content in the flow. So if I were to just replay the video once again, so this is the isosurface for 1e minus 4 by parts. We see the entrainment, and then we see a further spread. And the spread actually occurs fairly quickly. So at about maybe 30 to 50 convective time steps, sorry, not convection, at about 30 to 50 dimensionless time steps, we see that the entire wake is engulfed by that 1e minus 4 isosurface concentration. Okay, so now the summary and impact of our findings. So the contours actually depict that a high concentration by parts are entrained within the wake region. So of course you will expect that as the wake propagates downstream, right, we will see a smaller and smaller contaminant concentration. And of course, depending on what contaminant or pollutant that you're looking at, this may not be a problem. We are observing far downstream concentration values of about 1e minus 7 or even 1e minus 8, which we deem are not really an issue. And in fact, our sensors have trouble detecting that kind of threshold. But the concerning thing is that we see that further upstream in the wake of the building, we see these higher 1e minus 3 or 1e minus 4 levels of concentration, which can be quite disturbing depending on what kind of chemicals or contaminants that you're looking at. So this has practical implications in the real world scenarios, such as, like I mentioned, urban contamination dispersion patterns, which suggest that these local regions, right, or relatively higher concentrations may be dependent on different building heights, and also their dissipation time period might take longer to disappear. So these tracer gases might actually linger longer. Yeah. And also, ultimately, a surface level hazard could affect property and personnel at higher levels, such as the high-rise buildings, as this wake entrainment effect causes the contaminant to saturate the building's immediate exterior. So there are some considerations, of course, that involve our study. So currently, of course, we are only looking at the passive scalar. Obviously, knowing a chemical, we would like to move on to something like an Euler-Euler multi-phase simulation. But current observations, right, so far hint to us that the concentration levels are far less than 1%, and it is not expected for the errors to be significant, even if we consider the density differences. So this is including things like, for example, a chlorine leak, so or like even a typical tracer gas like sulfur hexafluoride, which is SF6. So SF6 is about 5 times the density of ambient air, I think. So even at less than 1% concentration, we don't think that kind of levels would affect the behavior of the bulk flow. And also, the last thing is that considering this is an urban environment, so the effect of urban heating and surface heating may actually induce a further verticality in that flow due to buoyancy effects, and that is not considered for now. So our simulations are non-isothermal. So like I mentioned, there are some challenges that we face. So the nature of this problem is highly three-dimensional. So it involves a horizontal propagation, right, followed by a vertical convection up the wake. So this is a bit challenging for us to come up with a quantitative way to assess the flow field. Perhaps we could do some kind of a 2-point, like a 2-point correlation or some kind of a method to study the effects of this, and also the effects of scaling and similitude from building scales all the way down to wind tunnel scales may not correlate that well. So the building that we're looking at is actually like 70 meters in height. So that may not correlate that well to the experiment and Reynolds numbers that we're looking at in the wind tunnel. And also the experimental method that we choose has to be non-invasive. So it can be, and even with a non-invasive method like LDV, it can be quite challenging to obtain a confident or reliable result for that. So again, just to move on a little bit more onto some of the future work that we are looking at. Like I mentioned, the validation could be done, could be improved. Instead of looking at the first moment statistics, we could perhaps look at spectral analysis and maybe some kind of a 2-point correlation. And also, I think we could somewhat improve some confidence in our LDV results, because yeah, the results I think are not that good considering the CFD results in relation to the CFD results. So we're having some troubles getting an adequate sample count based on a particular frequency, and also the precision of the focal zone becomes a challenge with such a small test section. Yeah, and also to better appreciate wake entrainment effects, perhaps we could also implement a time-varying boundary condition. So maybe like a pulse or step function to inject this, to disperse this tracer gas into the domain. Yeah. And with that, I think I just want to take 1 minute to thank our partners. So this is a research collaboration between the Singapore Institute of Technology, where I'm a research fellow at, and with our friends at DSO National Laboratories. So yeah, if you would be interested, just please find out more at the following websites. And of course, a big thanks to the OpenFOAM and open source communities. And I think with that, I run out of time. That's the end of my presentation. So this is me. I'm Benjamin, and this is my email.
Thank you, Benjamin.
Yeah, thank you. I can hear the applause. So yeah, thanks.
So we're having a bit of trouble with the link going down. I don't know if it's our end or in between or where. But I'm going to go around the room. If there's any questions, like you can speak.
Yes, please.
No questions? So so if nobody else asks a question, then I have to ask the question as part of the job as a session host. So in terms of the contaminant, are you putting actual contaminants into the wind tunnel? Are you trying to measure or have plans to measure contaminants in the wind tunnel scale to compare concentrations?
So the concentrations at the moment are different because the LDV's measurements that we are taking are just based on whatever sample count that we can get.
Yeah.
So what we are actually trying to design currently is to have this particle source located right where we want it to be. So this, as you can see in the picture, this is a bit tricky.
I see.
So we cannot possibly just move the probe there, and the probe itself would cause some kind of interference with the near wake. So we are thinking maybe perhaps we could mount this upside down, and then have the probe coming through. You know, so if it's upside down, then it will be from the ground up. Yeah, that's something that we are still working on. So this itself has its own challenges. And but to answer your question, no, there's no correlation between the particles that you're seeing here versus the one.
So you're using particles. Okay, I see what you mean. So there's the Architectural Institute of Japan. They've got a website with some data on where they use ethylene as the contaminant, and they can somehow measure that in the bulk volume. I don't know if you've looked at that.
Oh no. So Architectural Institute of
AIJ,
Japan.
AIJ, yeah.
AIJ. Okay, thank you very much. I'll go look for it.
That's we're trying to do something similar, and it's very difficult to find good data for
it is
comparing concentrations.
Yes.
Okay. All right, let's thank our speaker again. Thank you very much, Benjamin.
Thank you, everyone.